Okay, so welcome to everyone to this week's Origins Colloquium. And it's a pleasure, great pleasure to welcome Juan Farias back to Chalmers. Juan received his PhD from Chalmers in 2001, we're just remembering.
21.
Sorry, 2021, resetting the clock. Before that, he was a master's student at University of Concepcion in Chile. That's where I guess in that period, encountered Juan's work already on n-body simulations of clusters. Then it was his PhD here, actually first with a visit to Florida and then to Chalmers. And then since then, he's had a postdoc position at University of Texas in Austin with the Stellar Roughness Group, and since just the end of last year at McMaster with Alison Sill's team.
Yes.
So welcome, Juan. It's great to have you back here and hear about your work.
Thank you, Jonathan, for the invitation. And so yeah, today I wanted to share with you guys what I've been working in the last year. That pretty much connects to my time of working with Jonathan in my PhD here. So I wanted to introduce you to the dynamic cluster assembly framework. It's a framework I've been working these days, and how I'm using this framework to connect star formation to stellar kinematics. So so everything started with the Gaia. So we have in the last decade we have a revolution in astrometry with Gaia providing unprecedented accuracy in astrometry that lead a whole new ground of new surveys looking for stellar associations all around in our neighborhood. And these associations were before pretty much confused with the field stars before Gaia, and now we are characterizing them, their kinematics, their sizes. And what is interesting about the stellar associations is that, unlike the star clusters that are bound, stellar associations are unbound and they are dynamically joined for long periods of time. That means that what it means is that they might encode some information of the formation environments, and it's our job now try to extract this information. Now, observers is characterizing these distributions very well these days, but there is still a modeling layer, interpretation layer that is being developed these days and still in the early days, I would say. But for now, the only takeaway from this is that the present day stellar kinematics still can retain information about the star formation, and that's what we want to obtain. Now, these open questions of what kinematic information can survive the star formation, which observables retain memory of the formation environment, and can we use stellar kinematics to constrain star formation across different scales? And in order to answer all these questions, we first need to understand to understand how stellar dynamics shape these systems even before they are officially born, before gas explosion, just when they are being assembled. This brings me back to the work I did with Jonathan when my PhD here. We were doing this new thing where we were doing n-body simulations, but not as the rest of the community that normally assumed a star cluster just form instantaneously and then evolve, right? But in this case, we wanted to see what happened during the formation of the clusters. For that, we take the tubular core model. We have this model, this cloud of gas that we gradually transform into a star cluster at different paces and star formation efficiency at different speed. That was parameterized with star formation efficiency per 3-4 times that you see there. But all this to say how the dynamical evolution, how much dynamical evolution systems have even before they are expelled from the gas. They expel the gas. So what happened as star formation takes longer? So very quickly, I just want to show you here we have the Wheeler ratio in the y-axis is the kinetic energy over the potential energy, in which 0.5 is when a system is in dynamical equilibrium. And then we have a system that, in this time normalization, I will show you the evolution, but it's normalized with the formation time. So the star formation ends here for all the models, depending on how long it takes to form. And if we form a system slowly, for example, here, you will see the dynamical time of the system, the crossing time, is very small. It's this bar over here. That is how long it is. So that means that when we form a star, the star can relax and evolve with the system, and then we form another, and these stars form in a sort of equilibrium way. You see, it's very close to equilibrium all over the formation. But if we start forming clusters more fast, in a more rapid way, you see the crossing time now is longer in relation to the actual physical formation time. Well, the system had less time to relax, had less time to evolve. And as you see, they pretty much in these models, they are more supervirial by the end of the formation time. So the only takeaway that I want you to have from here is that the physical formation time, let's say 1 million years, 2 million years, is not the same as the dynamical time of the system. That the dynamical time depends on the density. The denser you are, the shorter your dynamical time. And this is important because it tells you how much time you have to evolve before star formation finish. And there are several dynamical processes that depends on this balance of these two timescales. And some of them can be reflected in the kinematics of today's associations. So before I show you my framework, I wanted just to give you a couple of examples of what I mean by kinetic memory, what kind of parameters we can observe. And one example, for instance, is the runaway stars. We can use runaway stars as constraints in the dynamical history of the systems. For instance, dynamical runaways are direct products of stellar interactions. And most of these interactions happens during the embedded phase, where the gas and stars live together, where they are dense. But how many runaway stars a system can produce is the question. In order to answer that, we calculate the interaction rate. This is just the interaction rate for a system to get accelerated at the velocity of a runaway star. And then we can integrate that interaction rate over time and over all the stars in the system. And we can obtain one number, that is the number of interactions that could produce a runaway star. Then we have the number of prediction. Then we just can compare to the actual runaway stars that we obtain in the models that I did with Jonathan, that I just showed you. And you see there is a kind of linear relation between the interaction number and the number of runaway stars that you can produce. Why this is important? Because this is one summary number. So there are many ways you can obtain this a given number of interactions. You can either be in a low density state for a long period of time, or you can be very dense for a short period of time to get the same number. What's important is this is one anchor we can use when we are modeling systems. I tested this in more modern simulations with MHT. This is Lucy Howell, a summer student at U in Texas. And we did the same in a better way with Starforce simulations, where I mean better because here the interaction rate was taken with global parameters inside the Harman radius. In the case that we work with Lucy, we use the local environment of each star and integrating the local environment of each star to reproduce the same trend. The only problem with runaway stars is that are rare events, and the statistics are always low with them. So yeah, but this is one example that observable that we can use. Right. So another important population of stars which kinematics is useful, not only for associations but for monocle clusters too, is the unbound population of stars. And here we are also working with Jonathan. We look into runaway stars from the ONC, but also combined or candidates that we found during that time with the already known population of unbound systems, in order to produce a distribution of velocities of the stars there. Now, what we did, for example, when you combine all this of this population, you see here the black line is our estimation from the ONC. And you see there are kind of two components where you have the central components that is defined by the velocity dispersion of the ONC. And the tail that you see over here is it depends on how much dynamical interaction it has in the past to produce those high velocity stars. And in the background, you see the models that from the models that I showed you at the beginning, that not all of them can reproduce these tails or either the shape of the velocity dispersion. So this is another way we can use kinematics in order to learn what is the path of the cluster. Okay, so these are just examples, but the question is that how star clusters really form and how these different timescales interact. And we don't even sure if we're mapping the right parameter space, because in the work, for example, that I did with Jonathan, we have to create a grid of models where we weren't very sure exactly where each timescale was. And the point of the model was to learn that. Now, but to learn more details about star formation, now we have the closed-scale modern MHD simulations that give us the insight of how the physics of star formation interact. Here I show you two examples that I've been working with, starboard simulations for my time in Austin. I work with this group, and I've been lucky enough to be working with the other group that do the same kind of models, the Torch collaboration. These are the models of Claude Cornelier. So what modern MHD simulations can tell us is that first they follow cloud collapse from the global collapse up to the formation of the stars self-consistently. They can include most of all stellar feedback processes and follow accretion and gas dispersal phase. So simulation can even produce stellar populations that are comparable to Gaia observations. So we can even try to use this to study kinematics, but there are several problems with that I'm going to show you. So basically now we have two different approaches. We have the MHD simulation approach to study star formation, and we have the embodied simulations approach to study star formation. That's pretty much just me. The MHD simulations, well, they have some pros. They have self-consistent environments. They follow cloud collapse, stellar feedback, turbulence. They have all self-consistent star formation. But the problem is that they are expensive. You only have a couple of them every time for each parameter. They are hard to interpret because it's an all-in physics. You put all physics, into the simulations to reproduce the environment well. And because they are expensive, the statistics are low. In the other case, we have embodied simulations that are controlled setups, which they follow stellar encounters very accurately, something that the MHD simulations not always have. We can follow this cluster for a long time, and we can follow do large parameter space surveys because they are not so expensive to do. The other advantage is that they had adjusted complexity. That means that we can control the setup, we can control the physics we want to put in order to understand what is going on. The cons is that, well, require lots of assumptions, and besides my own, there is no standard star formation prescription for that. Now, but both methods tell us different things. MHD simulations tell us how star formation happens, while embodied simulations tell us how star formation can shape stellar systems. There are actually no different approaches. I would say they are complementary approaches. And my work is the D-CAF, the framework I want to introduce today, is connecting these two regimes. And the idea behind D-CAF, the dynamical cluster assembly framework, is to obtain everything, all the information we can learn from MHD simulations or star formation models. Not only this, we can be analytical too. Everything we can learn from there and apply that into embodied simulations, so we can actually tell what are the consequences of those models into the stellar kinematic of associations. So I divide this, the process of doing all this work, I divide it in three phases: the analysis, the assemble, and the modeling phase. In the analysis phase is when we analyze the simulations. We obtain the structure, we learn about the gas how the gas evolved globally, the star formation statistics, the structure, the primordial stellar population, what kind of binaries they form, mass ratios, all that, depending on how detailed the simulation is. Then we use all that information to produce our models. We create a description, a background gas description for models. We create a star formation prescription for that and decide how we're going to do the sampling for the stars following the model. Then the modeling phase is when you use all this information and design your experiment, decide what you want to answer, which observables you want to get. Everything is done within the Muse framework. Muse is a framework in which you can couple different codes to follow the evolution. What you can do, you can follow star evolution, galactic environment, or even subgrid models if you want. Now, one thing I want to emphasize here is that this is not only designed for MHD simulations. In the case, for example, with me and Jonathan, we had an analytical prescription for the star formation. So we basically pretty much could ignore the first analysis phase and go direct into the assembly of model and complete the evolution. So now I just want to show you the first application we have to this, which is in this first application, we just wanted to see what are the consequences of the gas evolution before gas expulsion and during gas expulsion too, as you will see. So only analyzing these simulations is already very interesting. For instance, what I'm showing you here in the panels over there is the concentration parameter of the gas. What that means is that we take initial radii of the gas, and we get them fixed and just look how much mass gets into those shells in order to see how much the gas concentrates or maybe it leaves that region. And you can see, for example, in the door simulation, they get the central area, the 10% mass radius initially, get about a factor 3 more gas than it had initially. Before stellar feedback, clear up that gas and gas expulsion happened, right? Interestingly, the same happened in the Starford simulation, two very different frameworks. Well, it only happened at different scales. And in that case, we had a concentration parameter in the center of 2.5, but still the gas expulsion happened at some point and cleared up the gas.
Sorry, you're going to have to explain what is being plotted on the y-axis here.
It's the concentration parameter, is the mass fraction. So you have the mass initially at that radii, and then compared to the actual mass in the future. So that means that your initial 10% mass radius now have in the peak 3 times more mass in that initial radius. Mm-hmm. So basically it describes how the gas concentrates and then it blows away, pretty much.
Mm-hmm. Okay, I think I got it down.
So that is the analysis phase. So what we learn here? Well, gas evolves and considerably raised the central density, peaking at the moment that stellar feedback cleared off the gas. The collapse and monster formation in these models happens in about 1 free fall time. And the gas expulsion timescales is in both cases very similar. It's in the order of half a free fall time. But what is important about this is also that now we are not guessing timescale anymore. We can just take them, the timescales that we were guessing before, right from the simulation. Now, that is the gas. The analysis also, we have to do some analysis of the stars that are being formed. And we collect the locations of the stars where they actually form. You don't see them evolving because this is just the position of the star where they first appear in the simulations. Then with that information, we just can construct a density profile and a velocity profile of those particles. So that is in a first approach, though, we are using a spherical symmetry. We want to assume in the models we're going to use, we're going to just follow the radial distribution with assuming a spherical symmetry. But substructure is something I'm working right now. You can ask me later. We can discuss that later if you're interested. Now comes the assemble phase. The assemble phase is simple, using this information to produce our model. In this case, for the stars, we simply feed Plummer profiles to the density and a power law to the velocity distribution. And it's going to be our star formation prescription. We're simply going to sample stars from those distributions. For the gas, it's a little bit more complicated, but what we did is that we constructed constructed a parametric model for the gas. So in the first panel, you have this actual simulation data. The second panel, we feed Plummer spheres every time, every snapshot in order to construct that. And in the third panel, we use that information to produce a simple evolutionary model for the gas that we can directly include in our embodied simulations in a cheap and scalable way. So with all that, we come to the modeling phase. So this is the parameter space we did in this first work. Here you have the position of the simulation that we use as benchmarks, the star for and the Tor simulations. In these panels, we tested different freefall times. That means the densities in this direction. And we tested different concentration maximum. So the peak of the hill that you saw before, different star formation efficiencies, and different gas expulsion time scales as well. So these are the models where this is where we put model. We have the 10 simulations of each of them with all the combinations. That is about 1,500 simulations of where we keep the size of the cluster constant of those solar masses. You can see all the details in the paper. This is submitted. It's in the archive. You can look for that. I'm just going to show you a small fraction of those results. Just going in we're going to look at the low star formation efficiency. That are cleaner to interpret, so it's easier to see right now. So these are the Clayton models. This is the evolution of the Helmholtz radius. Now, what is important here is that now we have its evolution. One thing that we focused on this first paper was the expansion rates that I mentioned in the abstract. So now it's coming. And the way we compare expansion rates is that we simple fit to these lines, that each of them are different models. We fit a linear expansion. We fit a line, and the slope is the actual expansion rate of the region, right? This is something observers cannot see, but it's the actual physical expansion. So we try to answer what parameter control the expansion rate and associations. And the first thing here is that the formation environment is the one that set the maximum expansion rate in these systems. For instance, here, I showed you the slope of the expansion, the fit that we did, the slope of the fit. And we compare to this sigma max, that is the velocity dispersion of the stars right before gas expulsion begins. Okay, and what you see is that for the fast gas expulsion case, this is the expulsion time scale compared to the free fall time is 10%. This is pretty much instantaneous gas expulsion, and you see that the expansion rate of the cluster is just a direct linear relation of the velocity dispersion that the stars got before gas expulsion. But then, if gas expulsion take a little bit longer, half a free fall time, you see not all the velocity dispersion is transformed into expansion. It's got slow, and you might notice a little bit more scatter, and we will come that in the next slide. And then this is what happens when gas expulsion time scale is 1 free fall time, so it's low gas expulsion. So first, primordial expansion, the maximum of the expansion comes from the velocity of the velocity dispersion prior to gas expulsion set the velocity of the expansion, or the maximum, and then there is a damping produced by how long it takes the gas to be removed. Well, that comes a little bit late. So another way to see this, we're going to look into the scatter now, is that if here I'm showing the expansion rate, the measure from physical expansion rate divided by the velocity dispersion that we see, so pretty much the slope before, the slope is this ratio, that we can call as an efficiency of transforming velocity dispersion into expansion. So for instance, these models over here transform 70%, between 60 and 70% of their velocity dispersion into expansion. But now, if you see, we're comparing against the gas expulsion time scale in relation to the free fall time. But if we compare in relation to the crossing time of the stars, you see it change. And the reason this is changed, even though they are the same model, is because of the concentration of the gas. What happens when the gas collapses and concentrates before gas expulsion, if it concentrates a lot, that means that the local velocity dispersion of the stars is going to raise. If the velocity dispersion raises, the dynamical tends to get shorter. And that's why we used to have all the points in the same, they move in that area very far there, the ones that concentrated more in comparison to the ones that concentrate less that stayed behind. It's just a change in the local crossing time. And you see, when we do this, it's very easy to distinguish what the impulsive or adiabatic gas expulsion regime. By impulsive is when gas expulsion happens very quickly with relation to the crossing time, and the more adiabatic, the less expansion, and also the more chances to get a bound system behind you get. So what we get from here is that the crossing time regulates expansion efficiency, while the concentration of the gas regulates the crossing time of the system. So one question we have to answer, we have to ask to observers is how much can cloud concentrate before dispersing? That is one question. So now that is theory, theory. Now we want to see what of this is actually observable. Can we even measure expansion rates properly? So one way expansion has been characterized in association is using the gradient. This is the gradient, and the x is position in one direction, and then you have the velocity in one direction, and you get a gradient and a slope, and that tells you if the system is expanding or not. In this case, it's expanding. It will be collapsing if the slope is in the other direction. And normally, this is reported as an expansion signature. This particular metric is not very easy to compare between clusters, and the reason is because it evolves over time. And the reason is because since clusters are unbound, the velocity won't change too much. The velocity will stay the same, but the positions is going to grow over time because the cluster is expanding. So if you actually look directly to this over time, it looks something like that. So that's why you cannot just compare different clusters directly with this, because you catch them at different stages. But for this particular metric, one very easy solution is to multiply this metric by the half-mass radius of the cluster. If you do that, you actually transform that metric into an expansion rate. So you multiply it by the half-mass radius of the system, and you see all the lines after a few free-fall times. This is normalized. They become stable. That means that you can measure this at different times, and you're going to get a similar answer. But it's stable for the system that actually expand very fast. But the one that don't expand too fast is they have more evolution because they are more contaminated by bound systems. Now, this is one metric. And if we compare to the actual physical expansion, the one that we measure directly with the linear fit to the simulation, you see that actually this is a very well description. It's a very well proxy for the physical expansion rate. Now, this is one metric. Another metric that is very common these days is the outward velocity, the median out velocity. That means you calculate the radial velocity moving out of the stars in a system, and then you calculate the median, and that is reported as an expansion velocity. So that is another thing that I tested. We see that the pattern is very similar. After a few 3-4 times, it gets stable. So after that, you can just measure any time, and you will get the same answer. So that's good for comparisons. And if you compare to the actual physical time, it's also doing a fairly good job representing the actual expansion rate. So yeah, this is good. That means observers are measuring the right thing. That's very useful. So what just saying with this is that these expansion signatures are indeed measures of the expansion rate, and these are stable. However, though, there is a catch here. The only catch is that here I have all the information on the simulations. observers, for example, don't have the true half-mass radius. And these two trends needs to be calibrated against observational biases to see how can they actually represent the physical expansion rate. Right, so that is something we're going to do next. However, another thing is that if we look at, for example, this Stellar Crosser paper in 2023, they used yet another metric that is similar to what we did before, the expansion velocity, the outward velocity, but normalized by the velocity dispersion in that direction. And what they found is that apparently the systems that are young tend to have a higher expansion metric. This is not the direct expansion rate. This is more of a sign of coherent expansion. But as they get old, that metric goes down, and they interpreted that as the system losing their expansion signature, right? But if we look at the data, if we look at my simulations, and we look at this parameter, we see that the pattern is the same as before. They are stable after a certain time, fairly stable. And this decay in the expansion signature is not because of evolution, but it's more, it could be because of the galactic environment that removes some stars, and also depends on our own ability to find all the members, because the older you are, the stars that are moving away are farther and more difficult to find them. So that's pretty much the reason. However, there is one thing. However, what this tells us is that it appears there to be a window, a time window, where young clusters expansion signatures are useful, and we can actually use them for this kind of studies, right? If we are too far, too late, they are not useful, but if we are in the right window, we can actually use them. And well, what's the last thing I wanted to show? Yes. So now that the expansion rate is something that they actually measure physical expansion rate, and we are more sure, because we still have to calibrate this against observational biases. But we know that we can compare these values. I think it's time that we can actually produce, start doing start cluster population comparison, for instance, using the expansion rate. This is just an example, just to see what is possible to do. But here I'm taking all the data from 2018 that measure outward velocity in about 30 clusters, and just putting them in a PDF, and then compare to my models when I separate my models against different star formation efficiencies, and you see the different models produce different ranges of expansion velocities, in which Kuhn, for example, is kind of more consistent with star formation efficiency of 0.05 to 0.15 in comparison to the half, right? We don't have the tail of high velocity expansion. So this is the kind of studies that we can do now, and we're going to try to do in the future with the framework I'm using. And I just wanted to let you with my conclusions. This is simply that stellar kinematic can retain memory of the formation environments. Dynamical evolution during the formation shapes the future evolution of stellar systems. MIC simulation can provide us the necessary constraints on the interplay between the different star formation process. And we have constructed a framework that can transform those constraints into kinematic observable. So this is the framework I have, and I hope you guys enjoy. Okay, thanks.
Thank you very much, Mike. Okay, time for questions and discussion. So if you're in Zoom, just raise your hand to ask your question. We can hear your physical hand. And yeah, so any questions for Juan then? I see we have some observers online who measure these expansion rates.
Great. I would like to hear from them.
And as well as other theorists. I mean, so we can structure the discussion a little bit. So let's see. So the Starforge and the Torch MHD simulations, I think it's worth pointing out that they have their own parameter space and choices. and they typically don't. Well, perhaps you can comment. They're starting from isolated clouds. Are they isolated triangular clouds? Because there's a whole other framework of cloud collisions and making much more disturbed kinematics.
Yeah, that's
so they start with isolated clouds and spherical. And then there's another parameter, which is the degree of magnetic support, which would regulate the collapse. But I think what you're showing is that they all undergo this pretty global collapse quite quickly.
Yeah, and if magnetic field can actually affect that, is an important constraint and important result we have to consider. First, before going further, I would like to that this is a framework, and these two simulations are an example of analysis. So I would like to.
What do they do with primordial binaries, for example?
For example, they are very different. They both have two very different methods for that. For instance, torch. Let's start with StarForge. StarForge do accretion of gas from zinc particles, and everything is a star, and it will grow, and it may form a binary with another zinc, and that will be a binary. The problem is that in StarForge they use softening length for the gravity. That means that closed binaries, you cannot trust the population of closed binaries. Only white binaries are well modeled. On the other side, torch, their zinc particles are not single stars. Once they have enough mass, one of the zinc particles to produce a star, they go look into a list. This is the next star, and it pop out from the zinc.
So that's StarForge or torch?
That is torch.
Yeah. Well, torch has this crazy sinks that just go along and give birth.
Yeah.
Same zinc particle gives birth to a star, then
give birth
gives another star.
It could give birth to a binary.
Or binary, but a whole trail of stars is produced by this. It's
not the best, but
I'm being recorded. I should be careful what I say. Anyway, but it is a very strange, if you ask me, way of doing it. Did you notice these trails of?
We worked with that. I worked with that because at some point we. No, I'm confusing with StarForge. Sorry. No, yes, you can see that in the.
As torch.
In torch, after cloud collapse, you see all of the stars come like for the same regions. So yeah, different prescriptions give different results, and and that's the point of this. The point of the framework is to try to distinguish the consequences of these choices in the long term.
So how many, for example, when you make 1,000 stars in torch, how many come from independent sinks?
I will not say that from memory. No, but there are many things, and maybe you can have an idea if I show you the animation here. It's not the animation of the evolution, but at least you see where they are.
I can kind of see them, but
right.
It's nice talk, thank you. And
Adam particles is from the torch group. Yeah, please add a clone.
Yeah, sorry. Yeah, it is amazing talk, and here is in torch. Thin particles depend at resolutions. This is hydrodynamic resolution first. If your resolution level is high, here will form it is more thin particles. Which one it is enough density for it is Jeans length criteria. And after it is Joan saying that it is giving from list, and it is when it is thin particles mass is enough for doing enough for this list, and he's forming some stars.
But each sink is making a trail of particles, which in some sense, I guess, is a bound, could be a bound subcluster then. Is that right? Or is there an extra?
I don't know, because here is inside this accretion, sink accretions, here will form stars position and the velocity randomly. Here is not doing some boundly, I mean.
Okay. Did you have a particular question then for Juan to follow up on here? Or is that more just the explanation of the torch framework here?
Sorry, can you repeat the questions?
I'm just asking, do you then have a particular follow-up question for Juan? Or is that more just explanation of the torch framework?
My question, I have one question about this. What is n-body simulation are you using? And what is your future plans? Because I'm working now with n-body simulations all done, and I want to continue these simulations with n-body, and I'm analyze now. It is when it is correct way to it is change simulations to n-body because
Yes. So
because potential is sometimes will be very important for, and we can't go n-body simulations. Yeah.
So you're saying you have this torch simulation you want to continue with n-body after the finish, right? Is that right?
Yes.
Yes. Yes. Actually, that is something that in my group there is a person doing the same thing too. What At the difference of the Starforge, in the torch simulation, we didn't need to do too much work after the simulation finishes because the binaries that were there were already correct. They were already correct orbits. They had already correct orbits. The only thing you had to be careful is that the gas is already left the system. Otherwise, you will have to do something with the gas, some modeling. Otherwise, you would have like a jump.
But I thought the whole point of Torch was to do the hydro and the n-body together.
Yes, but you have one simulation then. They're very expensive.
Okay, so you're just saying that.
I'm saying it's not enough.
So but have you compared your ensemble n-body results to their individual n-body results?
Yes, at least for doing this was part of the benchmarking. Now, I just want to remember though that this is the only thing that we wanted to get here was the global evolution. So some differences are there. But for instance, we have this is in the bottom you have the Hartman's radius of the stars, where the gray is from the star force, and here the gray is from the torch, the original simulation, and then you have my models. So the idea of this was to get the scale right because we are ignoring a substructure, which is very important. And you already can see that the way how stars form really make a difference for the expansion rate. For instance, in the torch case, globally they form very similar to the way that we form in stars, like in a more central concentrated, more like a homogeneous concentrated way. And the expansion rate was very, very well described. In the case of star force, though, they formed stars like in a more coherent downfall, and then that means that when gas expulsion begins, they actually end up with a more coherent velocity, and that transformed in a higher expansion rate. What we are not sure though yet, because now we're only look at the evolution of the gas, is if this is caused because of the coherence collapse, or is caused by some problem of the close encounters because of the softening. So that is something we need to investigate in the next paper.
My memory is... Yeah, go on, Adkan.
Yeah, here is, you are saying it is some more information about gas explosion time. And in my case, we see that it is in simulations, it is explosion time depend at feedback effects and what is feedback channels you add in your simulations. If you add, for example, it is jets feedback effect, and here is gas stars will survive together with gas a long time, and here is last, it is after 8 for 4 times 2 can form the stars. It is something like this results I get just last week. Yeah, it is.
That's great. That's great.
It will be very interesting. Yeah,
actually, that is something very interesting and something that
also it is very important.
I only analyzed 2 simulations here, but I have more in the back. I have from Pollack, for example. I'm working on them. Let me go up to the parameter space. For maybe coincidence, we have that Starforge and Torch, these 2 models, have gas expulsion time scale very close to 0.5, and I'm very sure that will depend on the feedback mechanisms you were using. And if you have simulations that populate this differently, I would be happy to actually see them and include it in the framework. Because it had great consequences for the later.
Let me do one more follow up on the theory, and then we should maybe come to observational tests. But my memory of Starforge is they did not produce too many bound stars.
Yes,
but you are leaving a remnant bound cluster, right? In many of the simulations, or
depends. Yes, it depends on the parameter. Depends on the.
So that
in some of them, yes.
My question then is more. We talk about expansion rates, but of course, if there's a bound cluster, then that's not. Well, it may be expanding a little bit, but the expansion rate will be much less than the unbound population. But more generally, we should be looking for the bound clusters attached to every expanding population. And so this, in some sense, relates also to Joe, who's online here, but also, I don't know if you've considered connecting properties of the bound cluster with the expansion rates.
I haven't done it in this work, but I think but you're right. I mean, the more bound, the more contaminated expansion, and it depends of what mass radius you look, the expansion rate that you get from the system. I use 0.5. Do you know half mass radius for cases standard?
What fraction of stars are left in a bound cluster of 10 million years in any of your models?
It depends on. I mean, it's a parameter grid. You have to choose one number, and it's a classic lowest star formation efficiency that produce maybe no bound cluster at all.
But is there a bound? Is the bound fraction on one of these graphs?
No, because this is the initial conditions. I can show you the bound fraction, but that is in the paper. But it is it's actually quite interesting. Let me show you. Actually, I found like 3 regimes with that. Let me see if I can explain this. These are the typical. This is the bone fraction that we get as a function of star formation efficiency, local stellar fraction, that is star formation efficiency within the half-mass radius, and the gas expulsion timescale. And you see, when gas expulsion is very fast, the only thing you care is the local stellar fraction, the star formation efficiency inside the clusters. But then if gas expulsion is low, then it depends of how much gas you concentrate in the center. So it depends more on the gas expulsion timescale in comparison to the crossing time, you see. And in the middle is kind of it's a phase between both models. So it depends on which regime you are in gas expulsion. What is the parameter that best describe the bone fraction of the system?
But you have quite high fractions here sometimes.
In some of them, yes. They are quite consistent. This is torch. They are consistent with the torch simulation.
So that means every expanding population that is found should have some kind of bound cluster.
Maybe not. I mean, some kind, yes, maybe. I mean, we have some, for example, in Starforge, we have a bone fraction of 10% or even less. But some bone system might still get behind, and even more with substructure. If you get substructure.
How much it is virial ratio here? It is virial equilibrium or it is super virial?
That is another. Yes, that is the other. That is a great question because that also depends on the. Let me go here. That depends on the simulation, right? If you remember from the talk, I said that I give Plummer spheres. I collected the formation of the location of the star and get a Plummer sphere and then a velocity scale, right? I actually compared those scales to the scale of the cloud, and while I didn't calculate the virial ratio, I did get pretty much the same relation between the scale radius of the Plummer for the stars and the scale radius of the gas, and they were a fraction of each other. That was very similar. And the same thing happened with the velocity scale. If you compare the velocity scale of the stars in comparison to the velocity scale of the gas, In both simulations, I get a very close number, and that is, I mean, it was very surprising because I wasn't expecting that. But it depends on the simulation, what is the relation between the scale of within the cloud and the star population, and that will give you the bigger ratio. So it's not something I control, it's something I measure directly from the simulations to get the same scaling.
Okay. Well, these are details we'll have to discuss even later. Any more general questions from anybody else that was online?
Yeah, I have a couple if I may. I'm glad to hear, Juan, that you think that observers are looking at the right things. That's a relief.
Nice to see you.
Yeah, I mean, you made a statement towards the end that the expansion rates are useful within a certain window. Do you have an idea of how large that window is, or if it depends on properties of the cluster?
Yes, I think, well, it will depend, I think, of what is the main source of this decay. It could be galactic environment. I mean, if you have a cluster in a wide orbit, very far from the center of the galaxy, that may retain the expansion signature for longer in comparison if it's close to the center. If it's expanding very fast, you may have less time to actually find all the stars that are outside. So from what I see from the closest paper is the only reference I have right now. It looks like it's something in general.
This graph seems very strange. This sigma r, does that include the expansion itself or not?
This is normalization of that. Yeah, I mean,
but let's say you had a shell of stars expanding out at constant velocity, then all the velocity dispersion, all the sigma r
will be small.
Well, how is sigma r defined? Do you fit the global expansion first and then subtract that off? And then is what's left over sigma r?
Yeah, it's a one velocity dispersion. I mean, you transform all the velocities into radial velocity.
Yeah.
And so you pretty much have one dimension, right? And then you get the velocity dispersion in that dimension, and that gives you sigma r. So if you, in your example, if all the stars are expanding at the same velocity, sigma r will be 0 because all the stars have the same velocity expanding.
So it's okay, right.
But
then how could if sigma, well, this late time behavior, this quantity is 0, I mean, and then it goes negative. So that
that could be errors. In my simulation, I couldn't find any even bone clusters that have negative.
Yeah. You also have global expansion, which will be positive. So it must just be error, contamination.
But this parameter is good. It's not good enough for measuring the expansion rate itself, but it's kind of tells you how coherent expansion is. So a high value of this, it just tells you the cluster is coherently expanding.
Yeah.
But
But it's difficult beyond 20 million years anyway.
Yes. It won't be reliable. But I believe what this shows is that up to 30 million years, we probably can do this kind of studies.
So do you have another question, Joe?
Yeah, I suppose it's possibly a matter of future work. I mean, one thing that I'm looking at a lot at the moment is asymmetry in expansions. And I guess at the moment you're giving a cluster a single expansion rate. I don't know if your simulations produce asymmetric expansion.
Yes, they don't.
Okay.
They don't. I actually measure them in the 3D direction and I take the average. But I think it's a very, as you see, this is just the first work of this, and asymmetry is something that we really need to get care of. And actually now the next step is actually including substructure. So we're probably going to get asymmetries there.
And your benchmark simulations will have asymmetries.
Yes, and I don't have it here, but I haven't get into detail with that yet. It's something I want to maybe we want to discuss that, Joe.
Because then I'd like to know from interpreting the observations as well. If you find asymmetric expansion, which expansion rate do you prefer as a timescale? Is it the maximum expansion rate or is it an average? That kind of thing. Yeah.
That's interesting. Yeah.
Can you remind us then what are the epsilon free fall? So the efficiencies per free fall time. What is that epsilon free fall history of the two of Starforge and Forge? Because in some sense, then once you have that number, you could bring it back to our original framework.
Yeah, I remember they're very low, under than 1%, but I will have to check carefully exactly what that is.
But is that defined? You can define it based on the initial gas density structure or the current one. Probably the current is the dynamically the best way to do it.
I could look into that. I could do a calculation, not by head, with my head. I'm not very good at that.
Or in other words, what is the star formation history, age spread and so on? And maybe Adeklan knows some of this.
Star formations in Torch will do it self-consistently, and it is depends. It is how gas collapsed and how it is how most thin particles was born. Yeah.
Right. But is epsilon free fall typically 1%, 10%, or closer to 100%?
I don't know. Here it is not constant. Here is
It's an average
different number.
Sure.
It's not really low.
But what is your stuff? How long does it take to form a cluster?
In the Torch simulation I'm working with, it's about 4 million years. In the Starforge, it's about 8.
Mm-hmm.
Yeah.
Okay. Any other questions? Now we're close to the hour, so any other questions for Juan?
No.
Okay. Anybody else online or here? Okay. If not, let's thank Juan again for a great talk and discussion.